Um, Now let's calculate Fx, the x component of force between two Lennard-Jones particles. So what we are trying to do is calculate Fx, x component of force between two Lennard-Jones particles. This is a very similar problem of what we did previously, where we wanted to calculate Fx between two ionic particles, which we said the Coulomb particles. So here when I say two Lennard-Jones particles, that means the particles, they follow the Lennard-Jones potential when they interact with each other. So when you want to calculate Fx, essentially what you have to calculate is gradient of potential with respect to the x component, and this is nothing but minus del u del r and del r del x. Now my u, as the question said, is described by Lennard-Jones potential. So my u between two particles would be 4 epsilon sigma by r to the power 12, the repulsive term, and then you have the attractive term sigma by r to the power 6. Here r is basically the Rij, the interparticle distance. So from here we want to calculate del u del r. So this is nothing but let me just simplify a little bit. So this is sigma to the power 12, which is a constant, and this is a variable, minus sigma 6 is again a constant, where sigma is the diameter. And now I want to calculate del u del r. So if you differentiate u with respect to r, what you look at is 4 epsilon is the constant term, so it stays there, and when you take the derivative with respect to r, so r to the power 12, so you get minus 12, your sigma to the power 12 remains here, and then you get r to the power 13. Likewise here you have a minus, and then r to the power 6 gives you minus 6, that becomes 6. You have sigma to the power 6 there, and it becomes r to the power 7. That's your derivative. And what is del r del x? R is nothing but x square plus y square plus z square to the power half. That is your r. So your del r del x would be 2x, and then del r del x. Okay, so you have half here. So you have half 2x, and then you have x square plus y square plus z square to the power minus half, and that leads to x divided by r. So therefore that leads your x component of force is equal to 4 epsilon, here I have a minus here, and here I am taking one minus out, so that gives me 12 sigma to the power 12 divided by r to the power 13 minus 6 sigma to the power 6 r to the power 7. So that minus minus gives me plus, and then I had x by r from del r del x. So if you rewrite, what you can write this expression as 4 epsilon x. So if you take 1 by r out, you can write x by r square, x by r square, and then you have 12 sigma by r to the power 12 minus 6 sigma by r to the power 6. Let's see if we got it correct. 4 epsilon 12 by x r square sigma r to the power 12 minus 6 x by r square x by sigma by r to the power 6. So that's your x component of force between two Lennard-Jones particles. Likewise, you can calculate the force between two interacting particles along the y direction, along the z direction, and so on. So now the question is, what is the relevance? What is the relevance of calculating the x component of force between the Lennard-Jones particles or between the Coulomb particles? That's because if you recall how we propagate our system in molecular dynamics is that we make use of two important expressions, and those are RT is equal to R0 plus V0t, where RT is my new set of coordinates, R0 is my coordinates where we started from, V0 is the initial set of velocities for the particles, right particles, and then we had half a v square, half a t square, half a t square. And then we had, so this was equation number 1, and we had the other expression A is equal to minus 1 by m del u del r. That's my equation number 2. So these two are the primary equations in my molecular dynamics simulations. Our ultimate goal is to get RT, which is nothing but a set of x, y, and zi coordinates, and that they basically define the location of each atom in your system, and when you put up all these atoms together, then you see your whole system. So our ultimate goal is to get x, y, z coordinates for each of the ith particle, and for that we need to get the x, y, z components of A, and to get that x, y, z component of A, you need to calculate force along x, y, or z direction. So you need to calculate these force components during your calculations, and those will give you the acceleration, and that when you feed in equation number 1, you get this new set of coordinates which give you a new microstate or a new conformation of your biomolecule of interest. So that was the relevance of calculating the force component. Okay, so the next thing what we will be looking at is something where we can calculate, where we can often different microstates of a system by another computer simulation method. So if you recall why we introduced MD in our discussion, is that we know that ensemble is comprised of a lot many microstates, and so those microstates are basically giving the microstructure of our system. And to generate the microstructure in a large number of my system of interest, we introduced molecular dynamic simulation. And this technique basically given us the clue how to generate different new conformations or different new microstructure of my system of interest.